Dr. Sarika Kalra. I am from Akgec college and as an associate professor. So today we going to deliver a lecture on testing of two winding transformer. It is related to before your lecture has been done in this topic only. So we continue with this testing. So first, in the previous lecture, it is of the subject of electrical machine 1 and KEE 402. So in the previous lecture, we have discussed one of the testing of two winding transformer, that is open circuit test and short circuit test, and with the help of this two tests, we are tried to identify the parameter, the transformer parameter, the efficiency and the voltage regulation of the transformer. There is a lot of testing which has been done in the two winding transformer, but here we are only discuss few of them, right? So in the previous lecture we have discussed OCSC test. Now we are going to discuss the Sumpner test, that is called the back-to-back test or the load test. So before start with this test, you have to know what is the importance of this test, that is the Sumpner test, or also it is called the back-to-back test, and why it is called the back-to-back test, and also it is called the load test. So if the suppose these are the contents where we have already discussed OCSC test, then the polarity test and the Sumpner test. So today we will take up the Sumpner test, because this two test already has been done in the last lecture, previous lecture. So back-to-back test, the importance of back-to-back test is to determine the maximum temperature rise in the transformer and to determine the efficiency. So when the transformer is fully loaded, then we can measure the how much temperature rise in the transformer when we full load the transformer. But if the transformer is at the low power rating, then it is easier to get you apply the low load, and you apply the full load at the transformer, low rating transformer, and you will easily get the temperature rise. But for a large transformer or higher rating transformer, it is difficult to measure the maximum rise in temperature, because you have to apply that much of load, suitable load, so that will consume the full load power, that will be cannot be available, transformer may not be available at that power of load. And the second, if the large amount of energy will be if you use the large transformer to measure the temperature, you apply the full load on the transformer, so most of the energy will be wasted during this test. So we avoid this the full load test in the large transformer. So the alternative is to use the Sumpner test, in which we haven't applied any load, but it work as a loaded transformer. So that test is called the Sumpner test. So a full load test on the large transformer is to be conducted to determine the maximum temperature rise of the transformer, which is called the back-to-back test, and also this back-to-back test is also called the Sumpner test. Because why it is called the back-to-back test, because in this you need two identical transformer, one connected with the other. How it is connected we will see later, and one transformer is working as a loaded with the another transformer, right? So because if the transformer is small, you apply the full load, and it is easily to get the efficiency of the transformer, and easily you will get the temperature rise. But if it is a large transformer, so it is difficult for because you apply you need some suitable load that will consume full of load power, so that is very difficult, and due to this large amount of energy will be wasted. So alternative check the maximum temperature rise in the large transformer is to use the back to back test, that is called the Sumpner test, right. So first we see the how this Sumpner test will takes place. So in this we use two identical transformer, that means they have their voltage ratio will be same, and we connect in such a manner, so the primary, if it is a primary is connected in parallel. You can see that if it is A dash, B dash, so this A will be connected to B and A dash will be connected to B dash. So primary winding will be connected in parallel and you apply the rated voltage, right, and the secondary will be in such a way, so it is connected in series, and the polarity of both the secondary winding in such a way, so that this voltage gives you the zero rating. That means it will connected in phase opposition, so that you will get here the zero voltage, because if you apply here the rated voltage, you will get the rated voltage here according to the turn ratio, because as you know the E1 upon E2 is equal to N1 upon N2. So here E2 you are getting depending upon the turn ratio, and here E2B, so you can say yeah, this is E21, suppose this is a A transformer and this is B transformer, right. So E2A and E2B, here you are getting the E2B when you apply the rated voltage. So here rated voltage also in the primary side, in this transformer A primary side, and this same voltage you applied here in the primary of the transformer B. So here you are getting the E2A depending upon the turn ratio, and here you are getting the E2B depending upon the turn ratio. And these voltage, because both the transformer we have chosen identical transformer, so these two voltage are same. Now if we connect this two winding in series in such a way that the polarity of this voltage this winding to this winding is opposite, so the resultant voltage here is the E2B or E2A minus E2B is equal to 0. So we put, or suppose we connect the voltmeter of the rating of 2 times of the secondary voltage, right. So if you just check whether this V2 gives you the 2E or 0. If it is give you the 2E, you just interchange the terminal, so that the this 2 voltage you are coming in the secondary will be opposite in phase, and V2 gives you the requirement is V2 gives you the 0 voltage. So that means it here you need to check the polarity of this the secondary windings, right. Now after that, this is the transformer A and this is the transformer B, right, and to measure the input voltage, the input current and the power, you need some voltmeter, ammeter and wattmeter connected here. Now this secondary is connected in phase opposition. Now you inject the voltage in the secondary side, where the secondary winding is connected in phase opposition or in series and phase opposition. So you apply the voltage here with the help of this auto transformer. So with the help of this AC voltage source, you apply the voltage. Same source you can use for the primary or the secondary, and in the secondary, because in the primary you are applying the rated voltage, and in the secondary you apply that much voltage, so that the ammeter gives you the rated current, right. So you just put the knob, just increasing the voltage from the 0 volt and reach up to that much voltage, so that this emitters gives you the rated current. Now the rated current is flowing here, so this rated current will be the secondary rated current, right? And according to the transformer action, this current here also you are getting the rated current, the rated current of the transformer A, and this also gives you the rated current of the transformer B. Now you will see this current can be shown here, right? This rated current is within this loop. If you see the Kirchhoff law, this rated current is within this loop. That means no current will go in this primary side, right? That means this wire carry only the no load current, right? Because in this you can see, if you apply the voltage, the reduced voltage, and you set the voltage in such a way so that this emitters gives you the rated current. So according to the rated current, this carry the rated current, this transformer A or B, both A or B transformer carry the input current, right? The rated current, right, or the full load current. So according to the transformer action, this winding also carry the rated current I2A, and this is also carry the rated current. So this will, so you can see this current will not affect the primary side, right? That means the power given by this wattmeter is rated voltage multiplied by the input current multiplied by the cos phi, the no load power factor, right? That means this W1 gives you the core loss. Consider as a core loss, because this power will be sum of the, because the wattmeter gives you the power which is drawn from the supply. So how much power is supplied from this voltage, because this winding carry only the no load current. The no load current, the summation of no load current, the transformer A no load current and the transformer B no load current. So this no load current is the summation of, you can easily know the summation of the core loss and the magnetizing current. So this wattmeter gives you only the core loss, right, because it is at rated voltage and your core loss will depend upon the voltage. So it will give you the core loss at rated voltage. So this core loss is of both the transformer. Right. Now we come to here. In this circuit you can see this circuit is working on at rated current. So the current coil of the wattmeter carry the rated current. So this wattmeter gives you the copper loss of both the transformer. Right. So with the help of the Sumpner test, you can see this will not affect this wattmeter reading. So that means one wattmeter which is connected in the parallel side, primary side of the transformer is give you the core loss at a rated voltage or at the rated value, and this transformer, because you are applying the voltage in that much voltage, so the emitters it carry the rated current. So it's the wattmeter current coil carry also the rated current. So this gives you the power, because here is very reduced voltage you are applying, it is creating the short circuit condition, you can say. So very reduced voltage is applying here, so core loss can be avoided, can be assumed assume as less as compared to the copper losses. So this wattmeter gives you the copper losses of both the transformer, right. So this W1 2 times of, suppose it is core loss, W1 gives you the P and W2 gives you the 2 times of P core loss at full load or rated value, because this will not depend upon the core loss, will not depend upon the load, this is the only depend upon the load. So it is at rated full load and this is a rated value. So W1 gives you the power loss, right. What about this ammeter reading IA1 gives you the 2I0, where I0 is the no load current of transformer of both the transformer, right. So it gives you the summation of 2I0, that means 2 times of I0. I0 is the particular no load current of transformer A. In a similar way, I0 is the no load current of transformer 2. So 2I0 is the total current which is flowing in the primary side, right. So these are some points. This will back to back test. The primary winding of both the transformers is connected in parallel and is supplied at the rated voltage and frequency. As I said, the voltmeter, the ammeter and the wattmeter are connected in the input side. As I said, this is connected in the input side. The secondary winding are connected in series with the phase opposition polarity, which can be determined by the voltmeter. So the first step when you are performing the Sumpner test is to first check the polarity of the secondary, right. Then only you can able to perform the Sumpner test. So this must be the polarity must be in the phase opposition. So the phase opposition polarity. So this wattmeter, the range of this wattmeter you are connected, which is sum of the 2 voltmeter, right. Because in case suppose it has the same polarity, so this wattmeter able to measure the voltage of this both the transformer, right. That's why we are V2 we are connecting summation of, the range of V2 will be summation of both the voltage of the secondary winding, both the transformer of the secondary winding. So secondary winding connected in series and phase opposition polarity, which can be determined by the V2. As I said, the range of V2 should be double the rated secondary voltage of the either transformer, because either transformer, why it is called why it is written as either transformer, because both the transformer are identical, right. So in order to check whether secondary winding connected in series opposition or not, any terminal are connected together and the voltage being measured between the remaining 2 terminal using the voltmeter. As I said, like if this V2 is coming 2 times of secondary voltage, then just interchange the terminal, just connect C to A and B to D, just connect C to A and B to D, then this will give you the 0 reading. So in this way you can check the polarity. you can easily change the polarity. If the voltmeter V2 shows the 0 reading, then the two windings are in series opposition and the terminal A and D can be used for the test, as I said here, right. So, if the voltmeter V2 reads the value which is approximately equal to the double of the secondary voltage of either transformer, then secondary winding of both the transformer acting as in the same direction, then terminal A or C being connected together and the terminal B and T are to be this is the agar if this give you the 0, no need to change the terminal. So, this is the procedure how we perform the, this is the working principle or the procedure how we perform the back to back test. So, if the primary winding is connected in supply, the total voltage across the two secondary winding which are connected in series would be 0, as I previously mentioned here. So, thus no current flow in the secondary winding and hence they act as an open circuit. Like when this voltage is 0, that means there is no voltage difference here, that means no current will flow here. So, this circuit will behave as a open circuit, right, because you are changing the polarity in such a way that V2 will be 0. So, if the voltage is 0, there is no voltage difference. If there is no voltage difference, no current will be flowing here, that means it is working, there is no voltage, no current here, that means this transformer, setup of this transformer working as a open circuit, right, and you apply the rated voltage. So, it is similar, you can say open circuit test, right. Open circuit, hence the reading wattmeter W1 gives you the iron loss or the core loss. The iron loss is the summation of the hysteresis and eddy current losses. So, total losses, iron losses you are getting from this arrangement and at a rated value, right. Now, a low voltage is applied to the secondary circuit with the help of regulating transformer or you can say it as auto transformer, right. With the help of this auto transformer, you can apply the variable voltage to the two winding of the main transformer. So, low voltage is applied to the secondary circuit with the help of regulating transformer, which is also excited by the main supply, right. So, you are giving the low voltage here with the help of this AC voltage source, and this is the auto transformer. With the help of auto transformer, you are applying the low voltage, right. The magnitude of the supplied voltage is adjusted till emitter gives you the full load current, as I mentioned, right. So, this secondary current produce a full load current in the primary winding which flow through the primary winding and the main bus bar shown by the dotted line, right. In this case, you can see whenever this winding carry the rated current according to the transformer action, this winding also carry the rated current. So, it is but flowing in within this loop only, right. So, it will not destroy this open circuit arrangement. So, this will gives you the, that is why you are able to get the losses, the iron losses with this wattmeter, right. So, therefore, the transformer acts as operating as a full load because you are applying the rated current. So, this arrangement you can say, I am just this arrangement you can say work as a short circuit, right. That means fully loaded. You are applying the full load, the rated current. So, now the transformer is fully loaded, right. Therefore, the transformer acts as operating under full load, as the wattmeter W2 gives you the full load copper losses, right. So, the total no load current of the two transformer is measured by the emitter A1. Therefore, in the back-to-back test, two transformers are fully loaded, but the power drawn from the supply is that necessary to supply the losses of the both transformer, right? That means this two transformers fully loaded, because inside this transformer both are carry the full load current, but it will not affect here, because this carry the only the no load current, this carry the rated current. So even though it is fully loaded, the power drawn from the supply is not as much as equal to full load, right? So this is how you get with the emitter. You will get the no load current, and this wattmeter W1 gives you the total core loss, the W2 gives you the total copper loss at full load, right? So now full load efficiency you can easily find output divided by output, because here you are getting the losses of both the transformers. So if you are getting the efficiency, you are try to get the efficiency of individual transformer, you have to divide by 2. So individual transformer losses will be, it will divide by 2. So with the help of this formula you can easily get the efficiency of the transformer. So these are the some of the advantages of the Sumpner test. So low power is required to conduct this test, because as I said in the previous slide, whenever you are without conducting this back-to-back test, if you are measure the temperature rise, full load temperature rise of the transformer, because it is very important for the cooling purpose. So it is very important to get the temperature rise. So for this temperature rise you have to fully loaded the transformer. So to avoid this, we need this Sumpner test, back-to-back test, in which very low power is required to perform this test. Even though it is look like a fully loaded, it is the fully loaded, but low power is required, right? So you can easily get for a large transformer, you can easily get the temperature rise, right, at rated load. And full load copper losses and iron loss of both the transformer are determined. So this losses can be helped to determine the efficiency. Third, it increase the transformer temperature can be found. Increase in temperature, increase in transformer temperature can be determined, right? So on the basis of this, you can easily get the efficiency if you do if you have some numerical. So if the Sumpner test is performed, you will get this kind of readings and easily get the full load efficiency. But I have one numerical in which you are performing the Sumpner test, but these two transformers are not identical. So how will to deal with this problem? So I have just taken one numerical on the basis of the Sumpner test. Two single phase transformer of rating 10 kilowatt 10 kVA 230 by 400 volt and 10 kV 230 by 410 volt are employed for back-to-back test. The low voltage side is fed from 230 volt supply mains, whereas the auto transformer voltage regulator connected to the same 230 volt means feed 5 ampere in the series connected high voltage side, and for core losses is given 200 volt in each. So calculate the reading of wattmeter connected to the load. Is this transformer measured, is this setup will measure the core loss? Agar each transformer ka, if the each transformer core loss is 200, so if both if you are performing the Sumpner test and both the transformer are identical, so it easily you are getting 200 multiplied by 2, so it must be it should be a 400 watt. But if some of the if it is not identical, so there must be some difference in the core loss. So I just try to solve this problem. In this you can see that, suppose this is a transformer A, right? And this is transformer B. This is transformer B. Okay, so okay, no issue. So we are connecting two identical transformer are here. So one is A, one is B, and we are connecting here. It is given the low voltage side is fed from 230. So that means you are applying the rated voltage here. So this you are connected in parallel. Alright, these two winding are connected, primary winding are connected in parallel, and you apply here the 230 voltage, right? Now just listen carefully, and we connect here, we with the help of this auto transformer, you are applying the voltage here as the rated voltage, right? So you connect in such a way so that the polarity will be 0, and you apply here the, here also the rated 230 is the input voltage, and you apply here the reduced voltage so that the ammeter gives you the rated current, right? This is ammeter. Here you apply the 230 low, because it is saying the low voltage side you are applying the rated voltage. Okay. Now with the help of this regulator, same 230 mains feeds 25 ampere in the series connection. Now if you see the rated current, what about the rated current in the high voltage side? So it is 10 kVA divided by the voltage, that is 400. So it is coming out to be 25 ampere, right? That means 25 ampere the rated current is flowing in the secondary side, right? So it is flowing in the secondary side. So as this current will flow in the secondary side, the primary will start flowing, the rated current will start flowing in the primary side, and it is only flow within the circuit, right? Okay. So you can see that if you take this point, just a wait. What happened to this? Okay. So it is, you can see here, okay. So in this you can see that it must be the power must be 400, it is 400 volt, it must be a 400 volt, but current 25 ampere is induced in the primary. So primary current will be 1000 by, because in this you can see 25 ampere, so turn ratio will be 230 by 400, right? So the rated current will be according to this 25 ampere, but here the turn ratio will be 410 by 230, here the 400 by 230, here 410 by 230. So the primary rated current of transformer 2, the current will be bit different from the this. So you can see here this current is within this loop, right, but due to KVL you can see some of the difference of this current will go in the transformer, in the in the wattmeter, like in this case some problem is coming. So this is the current in the primary side of transformer 1, this is the current of primary side of transformer 2. So the difference between this two, 25 by 23, this will affect the wattmeter reading, right. So this current must flow through the emitter A1 and the current coil of W1. So this current must flow through the emitter A1 and the current coil of the wattmeter W1, right. So now the W1 effective reading will be V0, because the measure by the voltage is V, the rated voltage, the no load current, and the cos theta phi SC, right. So the power factor will be, as you know, the power factor will be, short circuit will be RE by ZE. So it can be here in the problem it is given like each transformer had the reactance equal to the 3 times of the resistance. So it is 1 by root 10. So power which is extra power which is affected by the because this two transformer is bit non-uniform due to the turn ratio, right. Turn ratio will be not similar. So due to this turn ratio will be not similar, the difference current which is flowing in the primary must flow through the wattmeter, okay, right. So that will affect the W1 reading. So it is coming out to be 79.1. So the core loss will be 200 minus 79.1 of each transformer, like sorry, it's 400 because 200 for each transformer, 400 total transformer. So it can be 400 minus 79.1 depending upon the how the transformer is connected, or 400 plus 79.5. So either it will reduce the core loss or it will increase the core loss depending upon the how the primary will be connected, right. So in this way you can easily solve the problem which is related to your Sumpner test. So I think now you must the idea about the how the Sumpner test has been performed in the transformer, right. So in the next session we'll come with some other lecture which is related to your transformer only. Thank you.